All right, welcome to a Parker Screencast on Newton's second law. The first law says that an object in motion will stay in motion, object at rest stays at rest unless acted on by an outside force. So basically, objects will not change their velocity unless you apply a net outside force. The first law is really a conceptual law or a qualitative law. The second law is when we get into the math. The second law essentially says F equals ma. And the third law, the first two laws talks about the forces acting on a single object. The third law talks about how objects interact with other objects. But today we are going to focus on the second law and the mathematical analysis of forces. So here's what Newton's second law says. This is writing it out. I prefer the mathematical form of the law, F equals ma. Remember, the units for m are kilograms. Units for acceleration are meters per second squared. Now, rather than saying a force of, say, 16 kilograms times meters per second squared is applied, we would say newtons. Then we have abbreviated kilograms, meters per second squared, to be equal to a newton. All right, if we are talking about the unit of the newton and writing it out, it's lowercase n. If we abbreviate it, it's a capital N. And of course, we're doing this to honor the man who first came up with the second law, Sir Isaac Newton. Now, this is a very, very important formula. So important that I call it the Tom Brady formula. Okay, it ranks right up there with the best formulas of all formulas, most essential formula. So, of course, I have to pick a personality that is equally as important. Yeah, moving on. Let's say I apply a 5 Newton force to the 0.84 kilogram air puck that you saw me kicking around the other day. And we know that it accelerates at 2.7 meters per second squared. What is the net force? Well, VFW is still in effect. We list out our variables. What are the things that we know? We know the mass, we know the acceleration, and identify the most important variable of all, force. Give that the question mark. Easy peasy. We know that F is equal to ma, that the force applied will cause the mass to change its velocity. Put in the numbers, 0.84 kilograms times 2.7 meters per second squared, giving us 2.3 kilograms times meters per second squared. But again, we can abbreviate that to 2.3 newtons. Easy peasy. Now remember, you can pause this at any time if I happen to go too fast. You should be writing this stuff down because it's good practice. The problems will get much harder than this, and it would be helpful to you to be able to work through the simpler ones as we build up to the harder ones. So if you need to, just pause. And yeah, here's it. We need to look at the fact that force is a vector quantity. Because it's a vector quantity, it has magnitude and direction, and it is well represented by the arrow. Just like we represented velocities with an arrow before, we can represent force with an arrow. And the acceleration is always in the direction of the force. So if I'm applying a force to the right, then the puck is going to accelerate to the right. All right. Let's do another example. Danger Mouse steals a large piece of Edam. Edam cheese is that cheese that is a big wheel or sometimes a ball. And he's going to roll it across the floor by applying a force of 5 newtons. If the cheese weighs 50 kilograms, what is the acceleration? Again, we're going to do our variables. We list out our variables. What are all the things that we know? We know force, we know mass, acceleration is a question mark, F is equal to ma, but this time we're going to solve for A. So divide both sides by m, and then I switch around the equation. So A is equal to force divided by mass. Force is 5 newtons, which is 5 kilograms, times meters per second squared. The mass is 50 kilograms. The kilograms cancel out, and we are left with just meters per second squared. So 5 divided by 50, it gives us 0.1 meters per second every second. So this means initially the velocity might be 0. 1 second later, it would be 0.1 meters per second. 2 seconds later, it would be 0.2 meters per second, so on and so forth. Okay, so we need to talk about the difference between mass and weight. Mass is the measure of the amount of inertia an object has, all right? It's a number, and it's really a measure of the amount of stuff that makes up an object. Weight, on the other hand, is the force of gravity that's acting on a mass. So an astronaut floating through space is going to have mass no matter where he is on the surface of the Earth, floating through space, on the moon, wherever. His mass will not change. But the weight will change depending on the location. If you're on the surface of the Earth, you would have a fairly large weight. In space, your weight could be near zero because the force of gravity would essentially be zero, depending on where you are, of course. Keeping that in mind, let's do a quick weight calculation. The force of gravity causes objects to accelerate at 9.8 meters per second every second. Remember, this is an acceleration. Well, if I have a mass of 68 kilograms, what is the force of gravity on me? Well, I'm going to be using Newton's second law to figure this out, but instead of a generic acceleration, I can use the acceleration due to gravity. So the force is equal to mg. 68 times 9.81 meters per second every second gives us a force of 667 newtons downward towards the center of the Earth. So really, I could put a negative here if I wanted to remain consistent in the fact that acceleration is in the downward direction, that gravity is in the downward direction. And again, we call this weight. Weight is equal to mg. So in your notes, you want to give a big circle that F is equal to mg, and really I should have a little subscript g here, standing for the force of gravity. So in summary, Newton's first law, this is a qualitative understanding. Second law says the same thing, but it's a quantitative understanding. It applies a formula. And then the third law is how objects interact with one another. But that's it for now. See you next screencast.